Okay, so let us start the today's session. In the last session, initially we have started with the types of systems. Okay, intensive properties, extensive properties. What is heat? What is work? Okay, so all those basic things we have started. Okay, now in this lecture, okay, we'll just move ahead in the same module. Okay, so now I will start sharing the screen. Okay, so see, in the last lecture, okay, we have derived the expression for work done. Okay, and work done was given by integration of PdV. Work done was given by integration of PdV. Work done during any process, it is given by integration of pressure into dV. Okay, so from that expression, okay, we understood that if you plot any diagram on the PV scale, okay, the area enclosed below that diagram will give you the magnitude of work done. Okay, so if you plot any process on a PV diagram and if you calculate area below that curve, so area below that process basically will give you the value of work done during that process. Okay, so now let us understand, okay, what do you mean by point function and what is path function. Okay, let us try to understand what is point function and what is path function. Okay, so let us see here. Okay, so let us consider point number point number 1. Okay, and this is the initial state. Okay, the point number 1 is the initial state where I have the pressure P1 and volume V1. Okay, at point number 1, pressure is P1 and volume is V1. Now, from point number 1, I need to reach to point number 2, where pressure is P2 and volume is V2. Okay, so point number 1 is basically the initial state. So from point number 1, I need to move to the final state, that is state number 2. Right now, see, you can move from point number 1 to point number 2. Okay, either through path A. Okay, you can move like this. You can move through path A. Okay, alternatively, you can move through path B. Okay, that is in straightforward you can move. Similarly, you can move through path C. Okay, so you can observe there are multiple ways, okay, to reach it to point number 2. Okay, so there are multiple ways, okay, from which we can move from state number 1 to state number 2, right? So see, so in every case what you can observe, the path is different. Okay, so when we see the path 1A2, okay, when we see the path 1A2, okay, and if you need to calculate what is the work done during 1A2, if you need to calculate what is the work done during 1A2, okay, we need to calculate area below that. Okay, we need to calculate the area below that. Okay, so area below that 1A2, area below that 1A2 will give you the value of work done during 1 to 2. Okay, so area below the 1A2 it will give you the value of work done during 1A2. Okay, is that okay, all of you? Let me know. Is that okay? Yes, is that okay? Yeah. Is that okay with this one?
Yes, sir.
Yeah. See, similarly, when you move through 1B2, okay, and if you need to calculate area, calculate the work done during 1B2. Okay, if you need to calculate the work done during 1B2, how you will calculate? You need to calculate area below 1B2. Area below 1B2. Okay. Similarly, when you move through 1C2, and if you need to calculate work done during 1C2, you need to calculate area below the 1C2. Okay, so this is the area which is below the 1C2. Okay, so now you might have observed, okay, when we move from 1C2, area is more as compared to the 1B2, okay, and is more as compared to 1A2. Okay, so in every case we are having different area. Okay, that means we have different value of work done. Okay, that means we are having different value of work done. See, I'm calling specifically as a work done because when you see the direction of this arrow, it is going downward. Okay, so when the arrow is going downward, okay, it is understood that it's an expansion. Okay, and whenever there is expansion, work gets produced. Okay, that's why I'm calling as work done. Work done. I'm not calling as work consumed. Okay, why I'm calling this as work done? Because arrow is going downward. That means it's an expansion. Okay, so see, work done during 1C2, it is 1B2, it is greater as compared to the work done during 1A2. Okay, so in every case we are getting different value of work done. Okay, that means work done will depends upon path. It will depends upon path. Okay, is that okay, all of you? Is that okay? That's how work done will depends upon path. That's why work or heat, they are called as path functions. I repeat, work done, okay, they are called as path functions. Is that okay? See, work done or heat transferred, they are called as path functions. Okay, is that clear?
Yes, sir.
Why work done it is called as path function? Because it will depends upon path that is followed, okay, during the process. That's why it is called as path function. Okay, now see, in the PPT it is mentioned as point function. Okay, I need to come to that point. Why it is called as point function? Okay, so have you understood what is path function? Let me know. Have you understood what is path function?
Sir.
Is that clear, or is there any doubt or difficulty still yet?
Sir, can you explain it again?
Yeah, I will just go to that. Here, all of you. See. When I move from point number 1 to point number 2, I can move through path A or through path B or through path C. Okay, now you understand, when you plot any process on a PV diagram, area below that process will give you the magnitude of work done. Okay, area, if you plot any process on a PV diagram, area below that process will give you the work done. Okay, so you observe that work done during 1A2, it is different as compared to the work done during 1B2 is different as compared to the work done during 1C2. So work done is different. Okay, that's why the properties like work, they're called as path functions. They're called as path function because work will depends upon path. Work will depends upon path. So when you move from 1A2, work done is different. 1B2, work done is different. 1C2, work done is different. That's why properties like work, heat, okay, they are called as path functions. Okay, so there are only two properties. One is heat and second is work. Okay, they are called as path functions because they will depends upon path. Okay, now let us come to this point, what is called as point function. Let us come to the point, what is called as a point function, right? Now see, when I move to from point number 1 to point number 2, try to understand. When I move from point number 1 to point number 2, okay, through path A or through path B or through path C, okay, I will be reaching to the same point. Try to understand. I repeat, when I will move from point number 1, okay, either through path A or through path B or through path C, I'll be reaching to the same point. Okay, so I will get the same value of pressure, I will get same value of volume, I will get same value of temperature. Okay, so whether it's a path A or path B or path C, I need to reach it to the same point. That's why the properties like pressure, volume, temperature, okay, enthalpy, entropy, internal energy, all they are called as point functions because these properties does not depend upon path. They only simply depends upon the point or state. Okay, so see, when you start moving from point number 1, okay, and irrespective of path, whether you go through A or B or C, okay, you will be reaching to the same point, that is point number 2, okay, where pressure is P2 and volume is V2. Okay, so this P2, this volume V2, it will not depend upon whether you are moved through path A or through path B or through path C, right? So this pressure will remain same at point number 2, and that is P2 and V2. It will not depends upon whether it is a path A or path B or path C. That's why the properties like pressure, volume, temperature, enthalpy, entropy, right? Internal energy, they are called as point functions. They are called as point functions. Is that okay? Yes, is that okay? All of you, is that okay? Let me know.
Yes, sir.
Okay, so see, you only understand there are only two properties. There are only two properties which are path functions, and those properties are work and heat. See, now you understand why the work is a path function, because what is the formula for work done? It is integration PdV. Formula for work done is integration PdV. So it indicates that when you plot any process on a PV diagram, area below that process will give you the value of work done. Similar case is going to happen with the heat transfer. Okay, because formula for heat transfer is integration TdS. Formula for heat transfer is integration TdS. So in the similar manner, if you plot any process on a TS diagram, TS, okay, TS it's called as temperature and entropy diagram. Okay, so if you plot any process on a TS diagram, area below that process will give you the value of heat transfer. I repeat, if you plot it on a PV, it will give you the work done. If you plot it on a TS, it will give you the value of heat transfer. Okay, so for PV, it's work transfer. For TS, it's a heat transfer. And both work and heat, they are path functions because they will depend upon path, okay, which you have followed while moving from initial state to final state, right? But when you compare this, okay, with the properties like pressure, volume, temperature, enthalpy, entropy, specific volume, okay, all those properties, they are called as point functions. Why they are called as point functions? Because they will not depend upon path. See, I repeat, I need to move when I start moving from point number 1, okay, either through path A or through path B or through path C, I will reach it to the same point, that is point number 2, where pressure is P2 and volume is V2. Okay, so that's why the properties like pressure, volume, temperature, enthalpy, entropy, okay, internal energy, okay, they are called as point functions. Okay, so this is the difference between what is called as path and what is called as point. So path functions depends upon path, okay, and heat and work, they are path functions, while point functions will only depends upon the points. Okay, so point is nothing but a state. So point function will only depends upon the point or state, and all the thermodynamic properties. I repeat.
Hello, sir.
Yeah.
Is the point function is very slow or a path function is slow?
Can you repeat? Can you repeat the question?
The process on
Yeah.
point function is slow or the process in point function is slow?
I still didn't get your question. Can you be it slow?
The process which is occurring in point function is very slow, no? Then compared to a path function.
No. See, whether the process is slow or whether the process is fast, it is nowhere related to the point function. I repeat, see, I need to move from state number 1, okay, and let's say, okay, I opted the path A, okay. In first case, I opted the path A, so I reached to point number 2, where pressure is P2 and volume is V2. Secondly, I opted the path B, still I am reaching the same point. Thirdly, I opted the point C, still I'm reaching the same point. That means the when you see the pressure and volume, whether it's a path A or path B or path C, I'm reaching it to the same point. Okay, where the pressure is P2 and volume is V2. That's why the properties like pressure, volume, temperature, they are called as point functions, because they will not depend upon path, whether it's A or B or C. Is that okay?
Okay,
Yes.
okay.
Is that okay? Okay. Now let us try to understand. Okay. Let us see this process. Okay. I'm plotting the same process on a PV diagram. Okay. So let us see this process. Okay. This is the initial point. Initial state is 1. Okay, from initial state 1, I need to reach it to final state 2. Okay, this is the initial state 1. I need to reach it to final state 2. So I will follow the path A. So I will follow the path A. Okay, now I will follow the path A. Now I need to return back to the initial state 1. So what I will do? I will now follow the path B. So see, overall, I will move from point number 1 to point number 2 through path A, and I will return back from point number 2 to point number 1 through path B. Okay, so when I move from 1 to 2, again back from 2 to 1, it completes a cycle. Okay, so when your final state is same as initial state, okay, that is basically known as cycle. Okay, so from 1 I have started, and I will be returning to again this state number 1. So that is called as cycle, right? So see, if I ask you, okay, what is the change in let's say pressure? How will you calculate? What is change in pressure? So change in pressure during the cycle 1A2. I repeat. This cycle 1A2B1. Okay, 1A2B1 is a cycle, right? You can see this one. 1A2B1. This completes a cycle. Okay, but this cycle, it consists of 2 processes. And which are those processes? The processes include 1A2 and 2B1, right? The cycle 1A2B1, it comprises of 2 processes, and those 2 processes are 1A2 and 2B1. Okay, so if I ask you what is the change in the pressure during cycle, okay, you need to add change in pressure during 1A2 plus change in pressure during 2B1, right? If I ask you to calculate either change in pressure or change in volume or change in temperature, okay, during the cycle. So cycle comprises of 2 processes. Okay, so you need to calculate separately the change in pressure or volume or temperature for every cycle, every process, and then we need to add. Okay, so change in pressure during this cycle is given by change in pressure during 1A2 plus change in pressure during 2B1. Okay, now see, what is the change in pressure during 1A2? So during 1A2, okay, initial pressure was P1, final pressure was P2. So change in pressure was P2 minus P1, right? Final state minus initial state. I repeat, during 1A2, okay, the initial pressure was P1, final pressure was P2. So change in pressure was P2 minus P1. Next, what is the change in pressure during 2B1? Change in pressure during 2B1 is, okay, final pressure, that is P1 minus initial pressure, that is P2. So that is written as P1 minus P2. Is that okay or not? Let me know. Is that okay?
Yes, sir. Yes, sir.
Okay, now see, when you add these two, okay, when you add this, okay, change, what you will get? You will get value equal to 0. You will get value equal to 0. Okay, so see, during 1A2, the pressure got decreased from P1 to P2. During 1A2, pressure got decreased from P1 to P2, but during 2B1, pressure again got increased from P2 to P1. See, it was initially decreased from P1 to P2. Now it got increased from P2 to P1. So what is changed? It's 0. See, no need to do this thing also, right? You can change it, or you can check it here. From 1 to 2, it is decreased. Again, from 2 to 1, it is increased. Okay, so there is no change in pressure. Similar thing, you can check it with the volume. Initial volume was V1. Okay, V1 got increased to V2. You can check. V1 got increased to V2. Again, V2 got decreased to V1. See, during 1 to 2, volume got increased from V1 to V2, and from 2 to 1, volume got decreased from V2 to V1 back. So what is change in volume now? It's again 0. So whether you take change in pressure or change in volume, okay, for a cycle is 0. Okay, so in general, if you ask me, okay, so I will say that See, cyclic integral of change in volume, change in pressure, or change in temperature is 0. What does it indicates? See, this integration indicates you need to consider all the processes. I repeat, this integration indicates you need to consider all the processes. This circle indicates it's a cycle, right? So you need to take cyclic integral of change in volume is equal to 0. Okay, what I'm asking is cyclic. See, circle indicates cyclic. This integration indicates integral. Okay, so cyclic integral of whether it's a volume or whether it's a pressure or whether it's a temperature, it is equal to 0. Is that okay? So same thing is applicable whether it's a pressure, whether it's a volume, whether it's a temperature, enthalpy, entropy, internal energy.
Yes, sir.
Okay. So let us start. Okay, so this is all about what? Point functions. These are called as, what is point function? Path function. Only 2 point functions, heat and work. Okay, and all the thermodynamic properties, they are path functions. And which are thermodynamic properties? Pressure, volume, temperature. Okay, so all these are thermodynamic properties. So is that clear with this one? Yes, is that clear? Yes, is that clear?
Yes, sir.
Okay.
Yes, sir.
So see, all this what you can see on the screen. Okay, this all I always used to draw the diagram. I used to write down that on a paper. Okay, but reason is now due to time constraint. Okay, I'm just explaining this thing. Okay, this is somewhat theoretical part. Okay, by just describing you. Okay, when we'll start with the numerical and derivations, actually we will derive it. Okay, so now let us move to the next point. Okay, now see this point. Okay, what is called as thermodynamic equilibrium? Okay, so see, thermodynamic. Okay, so you see, you can say that one body, it is in thermodynamic equilibrium with another body. I repeat, you can say that one body, it is in thermodynamic equilibrium with another body only and only when it is in mechanical equilibrium, it is in thermal equilibrium, and it is in chemical equilibrium with another body. Okay, so if one body, it is in mechanical, thermal, and chemical equilibrium with another body, then only you can say that that body is in thermodynamic equilibrium with another body. Okay, so if body is need to satisfy the thermodynamic equilibrium, it has to satisfy mechanical, thermal, and chemical equilibrium. Okay, now let us go to the point of mechanical equilibrium. Okay, what is mechanical equilibrium? See, as the name indicates, mechanical. Okay, so it is somewhat related with the force and movements. Okay, so see, basic idea is for every action there will be equal and opposite reaction. Okay, that means what? That system should be balanced. Okay, the system should be balanced. In simple, absence of any unbalanced force. Okay, there should be the absence of any unbalanced force. That means the same system should be balanced. Okay, let us take the simple example. Let's say a 20 kilonewton, it is applied to this simply supported beam. Okay, this is a simply supported beam to which the 20 kilonewton is applied, right? So see, if the 20 kilonewton is applied, obviously, okay, the reactions will be generated at the supported ends. Okay, and those reactions will depends upon the distance at which that 20 kilonewton is applied. Okay, so this 20 kilonewton will be balanced either as a 7 and 13 kg, 7 and 13 kilonewton, or it might be balanced as 10 and 10, it might be balanced as 5 and 15, right? So ultimately, okay, this 20 kilonewton which is going downward, it will be balanced by 20 kilonewton which is going upward. Okay, so that is the simple example, okay, how you can achieve the mechanical equilibrium. Okay, that means the system should be balanced, mechanically balanced. Okay, so this is all about mechanical equilibrium. Now let us go to the thermal equilibrium. See, name indicates thermal. So it is related with the temperature. Okay, so see, if temperature at any point within the system is same, then the body is said to be in thermal equilibrium. Okay, so if the temperature at any point within the system is same, it is said to be in thermal equilibrium. Simple. If you measure the temperature at any point and if it's coming same, you can say that the body it is in thermal equilibrium. Okay, now let us go to the next point. It is what is called as chemical equilibrium. Okay, chemical equilibrium. Okay, so see, if the chemical composition at any point within the system is same, it is said to be in a chemical equilibrium. Okay, so if you just check the chemical composition at any point within the system, okay, and it is coming same, it is said to be chemical equilibrium. In simple, there should not be any chemical reaction within the system. Okay, because what happens if there is any chemical reaction, okay, the chemical composition will change. Okay, and that should not be. So if you measure the chemical composition at any point within the system, if it is coming same, then you can say that the system it is in chemical equilibrium. Okay, so see, in brief, if you want, okay, so if any body it is in mechanical, thermal and chemical equilibrium with another body, then it is said to be in thermodynamic equilibrium with another body. So is that okay? Yes, is that okay, all of you? Is that okay?
Yes,
Is that
sir.
okay, all of you? Okay, so
Sir, ये chemical
okay,
equilibrium एक और बताओ ना.
yeah, I'll just go to that point. See, what is chemical equilibrium? Na? Simple. If you measure the chemical composition at any point, okay, what is chemical composition? Okay, like CO2, NO2, okay, SO2. So at any point, if you measure the chemical composition, okay, and if it is coming same, then you can say that the system is in chemical equilibrium. And see, when it is possible, when you will get the chemical composition at any point is same, when it is possible, when there is no any chemical reaction. Okay, so if there is no any chemical reaction, you will get the chemical composition at any point same. In that case, you can say that the system is in chemical equilibrium. Is that okay now, or still there is any doubt?
So okay, sir.
Yeah. Okay. Now let us move to the next point. Okay. Now see, now. Okay. See, this is very simple process. Okay. What is called as quasi-static process? Try to understand. See on the paper you will only see the diagrams. Okay. You will not see the explanation. Okay. So you properly pay the attention what I'm explaining. Okay. What is called as quasi? Okay. Quasi indicates a very slow. Okay. And static. Okay. It's somewhat stationary. Okay, quasi very slow, static it is somewhat stationary process. Okay, so see how to understand this process in a very better manner. Okay, so what I done, we have this piston and cylinder arrangement. Okay, you can see we have cylinder. Okay, and in the cylinder we have gas filled inside. You can see this is a gas which is filled inside a cylinder. Okay, and at the top we have this piston. Okay, this is a piston. Okay, and now on this piston, okay, what we are basically doing is we are putting a weight of 50 kg. Okay, single weight of 50 kg we are putting. Okay, now see, we are putting the weight of 50 kg, and now what we are doing is we are simply removing this weight of 50 kg suddenly. See, initially what I asked you, you put the weight of 50 kg. Now I am asking you to remove the weight of 50 kg suddenly. Okay. Then in that case, can you tell me what will happen? What is the possibility there? What will happen? What will happen?
Will expand.
The piston move upward.
Piston will move upward, right? Exactly, right. Very correct. See, what will happen when you remove this 50 kg weight suddenly? What will happen? The piston will move very fastly and it will strike the top dead center, right? Okay, whatever the top end is there, it is going to strike it, right? And see, whenever such process occurs, okay, then the path which the system follows while moving from initial state to final state, okay, it is a combination of non-equilibrium states. Okay, so what will happen? See, the piston will move from initial state to final state, okay, by following the non-equilibrium processes. Because what happens, you remove it suddenly. Okay, so when you remove suddenly, the piston will move very fastly, okay, and it will strike. Okay, now try to understand what is quasi-static. Now try to understand what is quasi-static. Okay, now see, instead of having a single weight of 50 kg, okay, what we'll do, that single weight of 50 kg we will replace by, okay, five strips of 10 kg each. What we'll do is that 50 kg by 5 weights of 10 kg. 5 weights of 10 kg. Simple example I'm doing. Okay, so these are the five strips of 10 kg we have. Okay, now what we'll do, we will start removing a single strip at a time. That means at a time we are removing 10 kg. Okay, so initially when we remove 10 kg, what will happen? The piston will move slowly. Okay, system will move slowly. Okay, again we will remove 10 kg. Again system will move very slowly. Again we will move it. Okay, so likewise we will move, and finally, okay, at the end, okay, there will not be any weight what is removed, what is remain on the piston. Okay, so at the end there will not be any weight. So can you tell me what difference you observed between suddenly removing the 50 kg weight and by replacing it with the smaller weights? Okay, so what difference you observed here? Okay, can anybody let me know what difference you observed? Yes, what difference you observed here?
In this
Sir,
first,
speed
the
is speed.
action,
Yeah, yes, you can answer, please.
so in this direct for in the 50 kg the single block, the answer which we get directly, fastly. But in
Yeah.
second process, the answer which we get, it is very slow, one by one.
Yeah. Now see, it is nowhere related to the answer. Okay, what you answered now, it is, see, like 70-80% you are correctly answered it correctly. Okay, but answer will not vary. Let me clear you. The reason is, see, when you remove 50 kg suddenly, na, what happens that you are not giving the time to the system so that it can adjust internally. Okay, you are not giving the time for the system so that the system can adjust internally. Because what happens when you remove it suddenly, okay, the properties are going to change drastically. Okay, or they just change it very fastly. Okay, but instead of that, if you replace this 50 kg weight by smaller weights, and if you start removing a single weight at a time, what will happen is, okay, you are giving the time for the system so that it can adjust internally, okay, so properties are not going to change fastly. See, when you remove 10 kg initially, okay, system will try to adjust itself. Again, when you remove 10 kg, again system will try to adjust itself. Okay, so that is what the quasi-static process is. Okay, so if you want me to define the quasi-static process, the definition is when the process proceeds in such a manner that the system remains infinitesimally close to equilibrium position. The system remains infinitesimally close to an equilibrium position, then such process it is called as quasi-static process. Okay, so in quasi-static process there will not be any traces, okay, either in a system or in the surrounding. Okay, so that is what the quasi-static process is. Now see, I'm repeating it. See, quasi-static process, it's a very slow process. And it's difficult to achieve such process. Okay, So I repeat, the quasi-static process, it's very slow process. It's difficult to achieve the process. You can call this process as an ideal process. Okay, you can call this as an ideal process. Now, question will be, if it's ideal, then why we are learning it? See, I'm telling you, it is difficult to achieve the ideal process, but we can move close to ideal process. Okay, and if you are able to move close to ideal process, okay, there are more chances to get more efficiency, right? So see, if you operate any power producing device, I repeat, if you operate any power producing device like turbine, like IC engine, okay, if you operate such devices on the quasi-static process, they will produce a maximum power. See, what we want a power production to be maximum, power consumption should be minimum. And when it is possible, when you operate it on a quasi-static process. So when you operate any power producing device like turbine, IC engine on the quasi-static process, they will produce some more power. Okay, but when you operate the power consuming devices like compressor, pump, okay, these are the power consuming devices. So when you operate these devices on a quasi-static process, they will consume less power. Okay, so that only we want. We want power producing devices to produce more power, power consuming devices to produce to consume less power. Okay, and this is only possible when you operate it on a quasi-static process. So is that okay? Yes. Is that okay with this one? Is that okay, all of you?
Yes, sir. Yes.
सर सर इसके अंदर सर आइडियल क्या है सर? मतलब लोड हम कम कर रहे तो थोड़ा थोड़ा ऊपर जाए, तो इसके अंदर आइडियल प्रोसेस क्या हुआ?
See, yeah. See, let us take the example of IC engine. Okay, let us take the example of IC engine. Okay, you can see the movement of the piston. Okay, movement of the piston, right? You can see the movement of the piston. Okay, you can see the piston will move very fastly, right? Piston always used to move very fast, right? Okay, but see, if the piston moves very slowly, what happens? When the piston will move very slowly, what happens? There will be the less friction between piston and the cylinder. Is that okay?
Yes, sir.
Okay, so if there is less friction, that means what? Less power will be wasted. Because see, whenever there is a movement of the piston, that movement of the piston should be utilized. Okay, but what happens? Some part of the movement of the piston get consumed in overcoming the friction between piston and cylinder. Some power gets consumed, okay, due to friction between piston and cylinder. Okay, but when you move very slowly, what happens? Okay, there will be less friction, and that power we can utilize. But that is not possible again. Nah? You can't move piston very slowly. Is that okay?
Yes,
so that is the reason why I'm calling these are the ideal process. See, if you are able to achieve it, obviously they will be beneficial. Okay, but they are difficult to achieve. That is the reason why. Okay, these are called as close to ideal process. Okay, we can just go close to them. Okay, we are not able to achieve them. Right? Is that clear?
Yes, sir.
Yeah. So now I'll just move to the next point. Okay, what is called as thermodynamic work? Okay, try to understand what is called as a thermodynamic work. Now try to understand. See, this I already briefed you. Okay, see, I will just give you some simple example. See, work will be always produced during expansion. Whenever there is an expansion, work will be produced. Simple. What is expansion? Let's say you have a steam. And if you allow that steam to flow on the blades of the turbine, when you allow the steam to flow on the blades of the turbine, what happens? Blades of the turbine will start rotating. Right? That means what? When the blade will start rotating, okay, obviously the blades are mounted on a shaft, so shaft will also start rotating. Okay, and you know that it rotates inside a north and south pole. Okay, that means it is further coupled to generator. So this is how the power will be produced, right? So this is what happens in the expansion. So see, work will be always produced. Whenever there is an expansion, work get produced. And how to understand its expansion? Obviously, the pressure has to decrease and volume has to increase. Okay. So when we move from point number 1 to point number 2, what is happening is pressure get decreased from 1 to 2, but volume get increased from V1 to V2. See, pressure will decrease from point number 1 to point number 2. Okay, that is pressure is decreased from P1 to P2, volume gets increased from V1 to V2, right? When such is the process, it is called as expansion, and during expansion, work get produced. Okay, now see, during expansion, work get produced. Okay, now see, now I'll just show you. Okay, okay, I'll just annote something here. Okay, as you can see here. Okay, let us see. As I told you, see, work, there is a concept of called as work transfer. The concept is called as work transfer. And what is work transfer? Work transfer indicates that work is produced, okay, or work is consumed. Okay, so there are two possibilities. Okay, what do you understand by work transfer? Work transfer is nothing but either work produced or work consumed. Okay, is that okay? Either work produced or work consumed. Is that okay? See, I'll just write down again. See, work transfer indicates that work is produced or work is consumed. Now see, if I say that work transfer is 30 kilojoule, okay, work transfer is 30 kilojoule. What do you understand? Work transfer is 30 kilojoule. What do you understand? So if work transfer is 30 kilojoule, you need to understand that work is produced. Okay, you need to understand that. Okay, just a minute. Okay, you need to understand that work is produced. Okay, work is produced. Because see, when you see the sign, okay, okay, it is positive. You can see for 30 kilojoule, okay, what is the sign? It's positive, right? For 30 kilojoule, see, work transfer is 30 kilojoule, so it indicates that the work is produced. Is that okay? I'll just write down work produces 30 kilojoule. Is that okay? Let me know. See, when I say that work transfer is 30 kilojoule, it indicates that work produces 30 kilojoule, right? But if I say it like this, see, okay, if I say it like this, okay, I say that work transfer is minus 30 kilojoule. Work transfer is minus 30 kilojoule. Okay, so you need to understand that work is consumed. Okay, work is consumed. Are you able to understand the difference?
Yes, sir.
See, when I say simple, work transfer is 30 kilojoule. Work transfer. Then you should recall that concept. What is work transfer? Either it's a work produced or either it is work consumed. Okay, work transfer is work produced or work consumed. So when you see the sign here, first case, it is plus. That means it's a produced. Okay, but when you see the sign here, it's the minus. That's why it's consumed. Work is consumed. Is that okay? Is that okay?
Yes, sir.
Yes,
Okay,
sir.
see now here, but what mistake you commonly used to do is, okay, you mention that work consumed is minus 30. It is not required. This minus sign is not required. See, I am repeating. Is that okay or not? See, I will just write down one more statement here. What common mistake you used to do is, okay, when you say that work, see, you used to write down that work consumed is minus 30 kilojoule. It is not required. This is a wrong statement. See, this is a wrong, because see, you already mentioned here it's consumed. It is consumed. So it is already understand that this is minus 30 kilojoule. No need to write down minus 30 here. See, when you write down minus 30, when you mention that, it is work transfer. Work transfer, it's a broad term. It's a produced or consumed. Okay. So in work transfer, okay, from the sign you can't mention like work consumed is minus 30 kilojoule. Not required. This is the wrong statement. Because this consumed word, it always indicates that it's a minus. Okay, so this is a wrong statement. Work consumed is minus 30 kilojoule. It's wrong. You can write down work consumed is 30 kilojoule, because consumed work word always indicates that it's minus. Is that okay? Is that okay, all of you?
Yes, sir.
Okay. Now let us come to the concept of heat. Okay. Let us come to the concept of heat. Now see how to understand heat. Okay. Now you can see on a PV diagram you have plotted the process. On a PV diagram you have plotted the process. Okay. So see, if I plot the same process, okay, on a TS diagram. See, this is a T diagram. Okay. This is S diagram. Okay. So if you plot it on a PV, it will give you work. Okay. So area below this process, see, you can see this area or this area. Okay. So this area will give you the work done. Why it will give you work done? Because you have plotted on a PV. You have plotted on a PV. So this is, in first case, this is a work of expansion. In second case, this is a work of compression. Okay. Now what I'm asking is, you now plot the process on a TS diagram. You plot this process on a TS diagram. So let me plot the same process on a TS diagram. Okay, so this is the initial point 1. I'll just take this point 1. Okay, this is a point number 2. Okay, and this is a process. Okay, I will move from point number 1 to point number 2. Right? Now see, when you see the area below this, okay, when you see the area below this, okay, area below the 1, 2, 2. Okay, just see the area below. This is the area which is coming below 1, 2, 2. So area below the 1, 2, 2 will give you the value of heat transfer during 1, 2, 2. I repeat. It will give you the value of heat transfer during 1, 2, 2. Because you are plotted on a TS. You are plotted on a TS. I'll just show you the formula. See, W is given by W during 1, 2, 2. Work done during process 1, 2, 2 is given by integration. Okay, this is the integration PdV. Integration PdV for the process 1, 2, 2. Integration PdV for the process 1, 2, 2. Similarly, okay, heat transfer during process 1, 2, 2. Heat transfer during process 1, 2, 2 is given by integration TdS. I repeat, integration TdS for process 1, 2, 2. For process 1, 2, 2. You can see two formulas you can compare. So when you plot it on a PV, it will give you work done. When you plot it on a TS, it will give you heat transfer. Okay, this is work transfer on a PV, and on TS, it will give you heat transfer. Right? So see, is that okay with the diagram? Have you understood the comparison? Have you understood the comparison? Yes.
Yes, sir.
Sir, explain again, please.
See, when you plot any process on a PV diagram, pressure and volume diagram, okay, area below that process will give you the value of work done. Work done. Because you are plotting on a PV. Similarly, if you are plotting on a TS, that is temperature entropy, area below that process will give you the value of heat transfer. For PV, it will give you work transfer. For TS, it will give you heat transfer. Okay, that is the case. Right? Now see again, as like work done. See, work can be produced, work can be consumed. Whenever work is produced, it is positive. Whenever work is consumed, it is negative. Similar case is going to happen with the heat. Right? So see, whenever heat is received, okay, so whenever heat is received, it is positive. Try to understand. Whenever heat is been received by the system, it is to be taken as positive. Whenever heat is lost by the system, it is taken as negative. Is that okay? Is that okay?
Okay.
See, I'll just write down. See, heat transfer. Okay. So see, what do you understand from heat transfer? Meaning of heat transfer is either heat is lost Okay, heat is lost, okay, or heat is received. Okay, or heat is received. Okay, received or extracted, abstracted. Okay, it is one answer. Okay, so see, heat transfer indicates that heat is lost, okay, or heat is received, or heat is received. Okay, now let us work on the cases as like work. See, when I say that heat transfer, okay, heat transfer is 30 kilojoule. Okay, heat transfer is 30 kilojoule. Can let me know what you understand from this. Heat transfer is 30 kilojoule. What do you understand? What do you understand from this? Sign is positive. That means what?
Sir, it is received.
Received, right? So I will write. I will write down here. Heat received. Okay, heat received is 30 kilojoule. Heat received is 30. Is that okay? Heat received is 30 kilojoule. Is that okay to all of you?
Sir, if heat is received, so in TS diagram the temperature goes high.
No. See, I just told you the again. See, I'm telling you, you just remember the formula, because in order to understand from where the formula has been came. See, you know integration PDV, from where it is came, we have derived that. But you
Yes,
don't
sir.
know integration TDS. Have I explained you the derivation for that? I haven't. Because that derivation we have in the second chapter. I don't understand. I'm just comparing it. See, if you compare now, then only you understand. See, the purpose to tell you that when you plot on a PV, it will give you work. When you plot on a TS, it will give you heat. Okay. Why by plotting on a PV, it is giving work done? For that, we have seen the derivation. Why? By plotting on a TS, it is giving heat transfer. That we yet not seen, right? So just now you understand.
Okay, sir. Okay.
See, because if I start explaining the derivation now, okay, then this point will remain here only. Okay. Now see, heat transfer is 30 kilojoule. That means heat received is 30 kilojoule, right? In the similar manner, if I say that, okay, heat transfer is minus 30 kilojoule. Heat transfer is minus 30 kilojoule. Then heat lost. Okay, you might see that heat lost is 30 kilojoule. Because see, minus sign, it should indicate that it's a lost. It's a lost. Okay, now I'm saying, see, you should never say that. Okay, you should never say that. Okay, heat lost is minus 30. Okay, it's a wrong statement. It's a wrong statement. Because see, you already written, it is lost. So it is understood that this term is minus. So no need to write down minus again in front of that. Okay. So this is wrong. This is the wrong statement. Heat lost is minus 30 kilojoule. It's wrong. If you're mentioning that heat lost, then you should mention that heat loss is 30. See, all of you see, heat lost is minus 30. It indicates that heat lost is 30. That's all. Okay, no need to write down again minus. Heat loss is minus 30 kilojoule. It's a wrong statement. Is that clear?
Yes, sir.
Okay. So see, I think, okay, with this, okay, we'll conclude the today's session. Okay, and in the next lecture, okay, we'll initially take some, okay, reversible cycle, irreversible cycle, and zeroth law of thermodynamics. Okay, so these are the only some descriptive part we will take in the next lecture. Immediately after that, we will be starting with the derivations. Okay, we will manually derive those derivations for 5 processes. Okay, first is constant pressure, constant volume, constant temperature, constant entropy, and polytropic process. Okay, so for all these 5 processes, okay, we will establish a relationship between pressure, volume, temperature. We will see the diagram. We will calculate heat transfer. We will calculate work transfer. We will calculate change in enthalpy. We will calculate change in entropy. Okay, so all these things we need to do it for these 5 processes. Okay, constant pressure, it's called as isobaric. Constant volume, it's called as constant isoporic. Okay, constant temperature, it's called as constant isothermal. Constant entropy, it's called as isentropic. And one more, it is there, it is called as polytropic. So for all these 5 processes, we need to see the derivations. Okay, so that we will see in the next lecture. So for today's lecture, we will stop. If you have any doubt or difficulty, you can just let me know. Okay, otherwise we can conclude.